Hi, welcome back. We are talking about section 5.4, applying definite integration, specifically distribution of wealth and average value. So we've tackled these first couple of learning objectives. We're going to work on deriving and applying a formula for the average value of a function in this last video from 5.4. So let's see if we can get to the right spot. Average value. So we've applied the distance between two curves and finding the area contained in that region in a couple of different ways. Mostly to begin with, just the actual raw computation. What does it look like to find the area of two regions that a geometric formula like rectangle or triangle doesn't really help us out for? And then we looked at a couple of cool applications of that, including the Lorentz curve. And this last one is applying definite integration in another way. So talking about the average value of a function, the goal here is basically to say, what is the most, I hate to use the word typical, but I can't use the word average because it's part of the definition, the most sort of typical value that you'd expect to find over some interval for a function. And the visual for me that is most helpful is basically something like if we were to actually take this curve and we took our graph of it, so whatever it looks like over some interval, and I'm supposed to picture that I have young kids, so I try to picture this like an aquarium where they've taken the normally calm water and they've kind of sloshed it around a little bit. So they've taken this aquarium and now here's the water level as it's kind of moved around. So the values, we have to pick some kind of interval to look over. But the idea with average value is basically, sure, my kids have kind of sloshed this aquarium and the water is not level right now, but eventually if we leave it alone and the water settles down, it's going to come to a constant height somewhere, I'm going to guess like that-ish. So this height really is the V that we're looking for, this average value. And so one way to think about it is that basically the area above it and the area below it are the same. And so when the level of the water, if you will, or whatever liquid, or however you'd like to think about this, settles down, it will settle down to this flat height. Another way to think of it is like if you had, it's always food for me, but a mound of cake frosting or something, and you were going to try to smooth it out to a level height, this is where that smooth height would get leveled out to. Anyway, I'm just guesstimating based on this, but what's great about that is it's literally taking this area, because that's what a definite integral is. So the integral from a to b of this function and spreading it out evenly over the interval b to a, or a to b. So the b minus a gives us the width of that interval, just the distance between these two things. And so v is the height. You take the area, divide out the width, and you get that average height. So I'd like to try this with a word problem, and then I'll leave you with the last one being a you try exercise. So we'll look at rate at which sediment gathers in the delta of a river. So you've got a river and stuff is kind of piling up at where the river spreads out and heads out into wherever, the ocean, I suppose. But it accumulates at a different rate depending on how far away from this study we go. So we're looking at length of time in years, and m is sediment measured in tons. And then the question we're supposed to ask is, what is the average rate at which sediment gathers during the first 6 months? So one of the things that's most confusing about these is that when we look at averages, the thing that comes after average, this is our f of x. So unlike the computations we've been doing before, where we're looking at area between two curves as being some new unit different from the actual function outputs, the average f, or function, or whatever, is the exact same thing as whatever we're given. So this is actually our f of x in this case, if we're looking back to our example from our definition from a minute ago. So we're looking for the average rate at which sediment gathers. And then the first 6 months of study, this is going to help us determine some values for a and b. So A and B. That's what this is helpful for. And really, if you look back at our definition, that's all the stuff we need. We needed to know the length of the interval, and we need to know a function that we want to take the average of. So average value for any function, again, just reiterating that definition from a couple of slides ago. So the average rate, okay, so first 6 months, I guess we have to be careful. X was in years. So the first 6 months would be in 0.5 years. And so there's our A, because we're looking from now until half a year from now. And then this thing right here is our f of x. I mean, it's got t as the input, so we're changing the letter there. But and then A is also represented here, B is also represented there. Again, we're just stealing that definition from up above. And that's all we need, really. So we need to know how to compute a definite integral. We're getting pretty good at that now. And then the only catch is that we're dividing out these units in front. Right, we don't have a rule that lets us do the integral of 3 over 2t plus 3, but we can get pretty close. And we can get right there if we do a substitution that gets rid of the complicated stuff in the denominator. So if we substitute out the 2t plus 3, that's the denominator, the derivative of that would just be 2. So du dt would be 2. We start multiplying stuff around and figuring out a way to substitute out something for our dt expression. So what we've got so far is that we could replace our entire dt thing with this expression. So we've got dt can get replaced with 1/2 du. We have that u can get replaced with 2t plus 3. So all of that is going to get replaced in the bottom. And then we'll have a nice tidy integral that we know how to compute. So we have the integral of 3 over u. That's something we're great at. You remember, if it's just a constant multiple, that 3 can get pulled out as well. Integral of 1 over u is just going to be natural log of u with absolute values, of course. But I don't think that will hinder us here. And then the other constant here, the 1/2, can also come out. So we'll end up with a net of 3 as a coefficient on this integral. I did put these reminders on the limits to tell myself that these are not u values. It's not u equals 0 or u equals 0.5. That'll become particularly important here in just a second. So I need to make sure that we go back. Once we've integrated, I need to go back to t's before we plug stuff in. So integral of 1 over u is natural log of absolute value of u. And here's that moment where I'm sure you are a stronger individual than I, but I would be tempted, without these t equals zeros, to just plug in 0.5 and 0 for u, even though that's not quite appropriate because these are t values, not u values. And then you'd immediately run into issues because natural log of u is not a real number. So you might think that this was broken when in fact it's got a reasonable solution. So one thing, I'm going to go back to the u's. So remember, this is really, u was really 2t plus 3. It was just a psychological device to help us compute this definite integral. But there is one catch here, that the absolute values have to go away. But remember that we're only looking for positive values of t. So no matter where we go with positive values of t, this expression, 2t plus 3, is going to be positive as well. So if you double a positive number and you add 3 to it, you're still going to have a positive number in the end. So in other words, these absolute values really, I mean, fine, I appreciate your hard work, absolute values, good job, but we don't actually need you in this case because there's no risk of this input being negative. So now that we're back to our actual t values in here, I don't feel the need to remind myself that it's t equals 0, t equals 0.5. I can just write these, and we can finally plug those values in. Plug in 0.5, plug in 0, and get ourselves a nice approximation. So 0.863. So the calculus has been accomplished here, but it is worth just checking in on the units with this. The units on our final answer are the exact same as the units on whatever it is we were actually integrating. And this is hard at first to process, I think. But remember, what we did was we integrated f, but then we also divided by the length of the interval. And the challenge with that for units is that here are units of whatever f is times the units of t. And so it seems like our final answer is going to get changed, have different units. But actually, since we're dividing by this as well, this has units of t. They're both, b and a are both time units in this case. So we are dividing out the units of time. And all that's left are the units of f when all is said and done. So it seems a little odd, but we really do end up with a value that's the same as the unit of f. But if you take a step back, if you think big picture, this is an encouraging thing, because we were trying to find an average value for f. It should be that our final answer has the same units as f. It's talking about a height of this graph. So we shouldn't get a different unit for average value than we would expect for units of f to begin with. And just to throw the visual on there, here's our graph of the original function, the rate of accumulation of sediment, that's the blue, and then its average value is this constant height. And then so you can kind of get the sense, especially with the computer algebra generated one instead of the one that I sort of sketched poorly by hand, the area above the average value and the area below are the same. So if this was that, aquarium that my kids sloshed around, eventually it would kind of settle down to be at a height of this, whatever, 0.863. So last thing for you to go for is another you try exercise. And here's where you would pause and try to compute this average value as your own little exercise. Okay, I'm assuming that you have paused and now come back. You've attempted this exercise and you're ready to try it out with me. So we're supposed to compute average value. So we'll start from our definition. And like most average value problems, the two things we have to identify are what is the thing we're actually trying to find the average value of. In this case, it's pretty explicit. This gets harder with word problems, as we saw from the previous example. We need to figure out what is the thing we're trying to find the average value of, and then what is the interval that we're operating on. So the actual function part of this is not too bad. The interval is actually the more challenging piece of this, but I think we can resolve this as well. The interval in this case is just where f is positive. And if we take a quick look at the graph, it does something a little bit like that. And where it touches the x-axis is out here at 4. So here's a graph of y equals f of t. So if we take that graph at face value, then the places where this is positive are between 0 and 4. And then the average value that we're trying to compute would be some constant height that goes, I'm going to guess there-ish. It's not halfway through the top because there's more area down here. But in any event, this is the V thing that we're looking for and we're not totally sure about yet. But the encouraging things are that we figured out f of t, which was given to us, and then now finally that other piece, the interval length that we're looking over. So b is 4 and a is 0. So we're looking from 0 to 4, and the thing we're trying to integrate is 2 root t minus t. So one reminder is that this can be more helpfully written as t to the 1/2 power, or t to the horrible scribble, as apparently I'm going to write. Must be the magenta, it just doesn't want me to write like that. So this is 1/4, and then we're supposed to integrate 2 t to the 1/2 minus t. Okay, we can use power rule on this, not too bad. So we'd have 2, and then this goes up to a 3/2, divide by 3/2, or multiply by 2/3 if you prefer, and then same deal with this guy. T to the first goes up to 2, divide by that new exponent, and then we're evaluating this from 0 to 4. So if we plug in 4, we plug in 0, I think we ought to get 2/3 as our answer. So that would say at a height of about 2/3, that would be the average output of this function on the interval from 0 to 4. Okay, so that'll do it for us, and we'll see you in the next section.